The moments of a distribution tell us something useful about the shape of a distribution. For example, the first moment is the mean, and it tells us something about the location, something about the center of the distribution, the center of mass, we might say. These two normal distributions both have mean 0, so they're both centered at the same point, 0. But they differ in an important way, and that important way in which they're different is captured by the second central moment, which is called the variance. And the variance tells us something about the spread of the distribution. The red distribution has a variance of 1, while the blue distribution has a variance of 4. So we see that the blue distribution is visibly wider, and that's captured by the variance. The third standardized moment describes skewness. Here the two distributions have the same mean and variance, so they have the same first two moments, but one has a longer right tail and the other one has a longer left tail, so they differ with regards to the nature of their skewness. If a distribution is perfectly symmetric, then it has no skewness, so skewness would be 0. The fourth standardized moment describes kurtosis. Kurtosis refers to an aspect of the heaviness of the tails. These two distributions have the same mean, variance, and skewness, so they have the exact same first three moments, but they differ with regards to the fourth moment, or with regards to kurtosis, or with regards to the heaviness of the tails. And moments don't stop at 4. Higher odd central moments capture increasingly subtle aspects of symmetry not captured by the moments of lower order. In other words, the 5th moment, the 7th, the 9th, the 11th moment, all of those will capture some aspects of the asymmetry of a distribution. And if a distribution is perfectly symmetric, all those higher odd moments will be 0. And higher even moments, such as the 6th, the 8th, the 10th, the 12th, these higher even moments become increasingly sensitive to the tails, so just like kurtosis, they will describe some aspect of the heaviness of the tails, something not described or not covered by the moments of lower order. So the point I'm trying to make is that moments tell us something very useful about the shape of a distribution. It is then natural to expect that if we saw two distributions that differ in shape, and if we knew that they have the exact same first n moments, so they have the exact same first moment, second, third, and up to n, then we would expect there to be some higher order moment which would explain the difference in their shape. And yet, this intuition is off. The two distributions that you are looking at right now have the exact same infinite sequence of moments. No matter what order moment you looked at, it would be identical between these two distributions. But how can that be? I mean, these distributions are obviously very different in shape, and yet that is not captured by any moment whatsoever. It is impossible to resolve this puzzle satisfactorily without introducing a specialist probability tool called the moment generating function, or the MGF. This concept is challenging, and its mastery will require mastery of everything we've covered thus far. So we'll need to approach it in a structured way. So here's the plan for the video. We'll start by revisiting the moments of a distribution, and we'll bring some order to our usage of the term moment, which sometimes refers to raw moments, other times refers to central moments, and yet other times refers to standardized central moments. There's a bit of a mess in the usage of the term moments, and we'll try to clean it up a little bit. Once we've achieved some clarity with regards to the term moments, we'll introduce the concept of a moment generating function. We'll start by doing something that is familiar to us since section 2.1, and that is forming random variables that are deterministic functions of another random variable. So we'll start with a random variable x, and we'll form another random variable that is e to the power tx, which is a deterministic function of our initial random variable x. It is a deterministic function for a set value of the parameter t. And since this newly created random variable is a random variable that is a deterministic function of x, we know how to calculate its expected value using Lotus, which is something we've covered in section 2.2 and the previous video. So we'll do just that. But this new random variable that we'll create, e to the power of tx, has two interpretations. It can be viewed as a deterministic function of the random variable x for a set value of t, or it can be viewed as a function of t. So in the second perspective on this random variable, we will view it as a function of t, and we'll remind ourselves that for a function f of t, we can express it as an infinite power series using the Taylor series expansion. And since we'll be interested in expanding around 0, for reasons I'll explain, it is this particular case of the Taylor series, when we expand around 0, which is called the Maclaurin series, that will be of greatest interest to us. We'll see that we can obtain the raw moments of a distribution in two different ways. First, using an algorithm of sorts, where if we want the nth moment of the distribution of a random variable x, we take the nth derivative of the MGF and evaluate it at 0. What you will get will be exactly the value of the nth moment of the distribution of x. Okay, that's sort of the algorithm, and we'll get some practice with it. But a way more elegant and comprehensive way of obtaining the moments is to write out the Maclaurin series of the MGF and then read off any raw moment of interest right off that series as easily and as readily as picking a low-hanging apple from a tree. But although the moment generating function gets its name from the fact that it can give us the raw moments of a distribution, its main utility to a trained probabilist, or we could say its main utility in practice, is somewhat disconnected from this moment generating fact. The MGF of a random variable is a Laplace transform of the PDF of a random variable, and since Laplace transforms are unique, it is not altogether unexpected that there might be a uniqueness aspect to MGFs. In other words, if you bump into an MGF on the street, you could ask, which distribution does this MGF correspond to? And in an ideal scenario, there should be only one distribution that would be able to claim this MGF. In other words, the MGF could be used almost as an ID for a distribution, much like the CDF, where if somebody called out a particular CDF, we know what distribution that refers to, and if somebody called out a particular MGF, we would equally know what distribution that refers to. But we'll need to proceed with caution. And that caution pertains to the fact that we need to be very clear when is it that we say that an MGF exists, or when is it that we say that a random variable x has an MGF versus does not have an MGF. Bigger picture, we'll just need to be careful about when the MGF can be safely mapped back to a single distribution. In other words, when the MGF can be used as an ID for a distribution, much like a CDF can be used for an ID of a distribution. We'll explore these issues by exploring the sum of three independent exponential 1 random variables. This sum itself is a random variable, right? And hence we can explore its MGF. We will then find that the MGF of this sum is the same as the MGF of a gamma 3,1 random variable. Can we then conclude that the sum of three independent exponential 1 random variables is a random variable that has the gamma 3,1 distribution? You see that we're trying to use here this ID property of an MGF. After we've covered all this ground, we'll return to our introductory question and explain how it is possible to have two distributions that look entirely different and yet share the same infinite sequence of raw moments. Okay, that's the plan. Let's jump right into it. Let's travel back in time for a moment. Let's go to the year 1921 when Felix Hausdorff, a mathematician, reached an absolutely incredible result. But in order for us to appreciate it, let's take a step back and set the context slowly. Imagine that we are interested in drawing the PDF of a random variable x. We'll start by drawing the real line, so positive infinity is this way, negative infinity is this way, and we'll pick a particular closed interval. We'll call it AB. So our interval of interest will be this interval, this closed interval AB. It is on this interval that now we want to draw our PDF. And suppose that we feel like drawing it this way, and we drew it in a way that the area underneath is 1, as it should be for a legitimate PDF, and then the PDF is positive everywhere. It's above the real line, so this is a legitimate PDF. Okay, now here's the question. We have this random variable x, and this random variable x has the PDF in green that we just drew. And we're allowed to build new random variables that are deterministic functions of it. So we are allowed to build any random variables that are deterministic functions of our original random variable x. But we're not doing this for fun. We're doing this with a goal in mind, and that goal is that some aspect of these random variables that we build needs to be informative about the PDF of the random variable x, the one that we just drew. Okay, informative is a vague term. How about we're looking for the set of random variables that are deterministic functions of our original random variable x, which would fully encode this PDF and which would uniquely identify this PDF. It would capture every turn in this PDF we just drew. It seems like an impossible task. And yet in 1921, the mathematician Felix Hausdorff did just that. He was focused on the random variables that are powers of x. So x squared, x cubed, somewhere here there's yn as x raised to the power of n, and this goes into infinity. And he was interested in the expected value of each of these, something that we call the raw moments today. And remarkably, he was able to show that the infinite sequence of raw moments fully and uniquely encodes the PDF we just drew here, the PDF of X. This is absolutely incredible. We could have drawn another PDF here in purple, and this one corresponds to a random variable W. Well, the infinite sequence of moments of W, the infinite sequence of raw moments, would fully encode that PDF we just drew. Let's highlight one aspect of the problem that makes this possible, and that is that we are looking at only PDFs that exist on a bounded support, on a closed interval AB. The raw moments of a random variable do not generally uniquely identify the PDF on any support if we're allowing it to go into negative infinity or positive infinity. But on a closed interval, this is true, and we'll see exactly why it's true. And one other qualification is in order here. The infinite sequence of moments of a random variable with a closed support uniquely identifies the CDF of a random variable, not the PDF. Just highlighting the fact that there is a CDF for every random variable out there, but there are random variables that have a CDF but do not have a PDF. Anyway, we've made the disclosures we had to make. It doesn't make this result any less incredible. But we've mentioned the raw moments once more, so it's time to clarify the distinction between raw moments, central moments, and standardized central moments. The raw moments of the distribution of a random variable x are simply the expected values of x raised to different powers. So for example, the expected value of x raised to the first power is the first raw moment, and that one has a special name. It's what we call the mean. The expected value of x raised to the second power is the second raw moment of this distribution. The expected value of x raised to the third power is the third raw moment, and so on and so forth. I brought the central moments into view as well to highlight the fact that raw moments are measured relative to 0, whereas central moments are measured relative to the mean mu. And notice that the second central moment is what we call the variance. Let's focus for a moment on the difference between the second raw moment and the second central moment. In this plot, you see the distributions of two random variables. So we have two distributions that have the same variance, the same second central moment, but different second raw moments. And recall we said that the raw moments are measured relative to 0. Notice that the red distribution, which has a mean of 0, is tightly clustered around 0. And so it has a lower raw moment than the blue distribution, which has a mean of 2. But its second raw moment is relative to 0. And since the blue distribution is overall farther from 0 than the red distribution, it will have a higher second raw moment. But imagine that you saw this picture and you want to communicate to your friend what it is that you saw in it. The first thing that we will say is that these two distributions have the same spread, and that spread is measured by the variance, the second central moment, where because we measure the variance of each of these distributions relative to its mean, we get a measure of spread that does not depend on the location of the distribution. And only after we would say that, oh, these two distributions have the same spread, would we mention probably the fact that the blue one is just shifted 2 units to the right relative to the red distribution. Both raw moments and central moments will have their uses, so we just need to learn what it is that each tells us. Okay, we mentioned the variance, and let's also mention the standard deviation. And the standard deviation is taken to be just the square root of the variance, the positive square root. And the advantage of the standard deviation is that it is in the same units as our random variable x, whereas variance is in units squared. So if x was measured in years, then the variance is measured in years squared, which not really sure how to interpret that, but the standard deviation is measured in years, just like the random variable x. So the advantage of the standard deviation is that it is measured in the same units as x, but notice that the standard deviation is not unitless. Unlike skewness and kurtosis, which we'll see in a moment, skewness and kurtosis are unitless. So how do skewness and kurtosis achieve their unitless status, so to speak? Well, notice that they go one step beyond central moments. Whereas central moments, being relative to the mean, account for differences in location, standardized moments, in addition to that, divide by standard deviation. We already mentioned that distributions that are perfectly symmetric have a skewness of 0, and not only is it that their third moment will be 0, but also the fifth, the seventh, every odd moment beyond that. Okay, and we could look at how asymmetry is measured by skewness, but that's actually a little tricky. So let's look at kurtosis instead, since I think there'll be more intuition there for us. I plotted here two normal distributions. Every member of the normal distribution family, in other words, no matter what values of parameters of the normal distribution we pick, for every member of the normal family, kurtosis equals 3, which is a little puzzling because if you take these two distributions, obviously the blue one has a much higher variance than the red one. For the blue one, the variance is 4, and for the red one, the variance is 1. So what is it that is measured by kurtosis with that value of 3? We said that it's a measurement of the heaviness of the tails, but we need to be a little more precise than that. The fact that these two distributions have the same kurtosis value means that their tail behavior relative to their own standard deviation is the same. Put differently, if we were interested in the random variable with the red distribution here, which has a variance of 1, and we are interested in the event that this random variable takes on a value greater than 1. And notice that 1 is one standard deviation above the mean, right? Because this distribution has a variance of 1, hence a standard deviation of 1. So if we go from 0 to 1, we've traveled one standard deviation to the right. So this event, let's call it A, is the event that this random variable takes on a value greater than one standard deviation above the mean. Now suppose that we're interested in the analogous event for the random variable that has the blue distribution. So the analogous event here is that we're interested in the event that the random variable with the blue distribution takes on a value greater than one standard deviation above the mean. The mean of the blue distribution is 0, its variance is 4, therefore standard deviation is 2, so the event of interest then is event B. These two events will have the exact same probability of about 0.1587. And this is precisely what the fact that these two distributions, just like any other normal distribution, have the exact same kurtosis value of 3, says that their tail behavior relative to their own standard deviation is exactly the same. We have defined raw moments among other ones, but we haven't seen anything that would help us explain why raw moments, in the case of a random variable that is defined on a bounded support and that admits a PDF, why raw moments would uniquely identify a PDF. What's the connection between raw moments and the PDF? Let's see that next. First, we'll need to remind ourselves what the Taylor expansion of a function about a point is. So given a function f of t, the Taylor expansion is f of a, so the function evaluated at the point a about which we are expanding, plus the first derivative of f evaluated at a divided by 1 factorial times t minus a plus the second derivative of f evaluated at a over 2 factorial times t minus a squared plus f, the third derivative of f evaluated at a over 3 factorial times t minus a cubed, and so on and so forth. And if we just took this a, the value of a, to be 0, then that expansion has a separate name known as the Maclaurin. So in that case, the expansion would be f of t equals f of 0. We're just replacing 0 for a plus f prime evaluated at 0 over 1 factorial times t plus the second derivative of f evaluated at 0 over 2 factorial times t squared plus the third derivative of f evaluated at 0 over 3 factorial times t cubed plus and so on and so forth. Now suppose that one sunny day we were fortunate enough to be contemplating the function f of t, which is e to the power of tx. And how might we have arrived at it? Well, perhaps we were interested to begin with in random variable x, and then we said, why don't we form another random variable, e to the power of x, which is a deterministic function of x. And then we said, what if we introduced a parameter t? So x is still a random variable, but t is a parameter. Okay, so let's see what the Maclaurin expansion of this function of t is. Well, in order for us to proceed, notice that we're going to need the derivatives. We're going to need the first derivative first. So what is f prime of t? The derivative of this expression here would be e to the power tx, and then by the chain rule we need to take the derivative of the exponent tx with respect to t, and that would be just x. Okay, so we get x times e to the power tx. Okay, now what about the second derivative, f double prime of t? The second derivative here would be the first derivative of this expression on the left, and t appears just once, right? So it'll be e to the power tx. By the chain rule, we'll have to take the derivative of tx with respect to t, and we'll get x. and then there's an x already waiting for us here at the bottom, so we get 2x's, so it'll be x squared. Okay, we're already starting to notice something interesting here. Notice when we're going to take the third derivative, we're going to get x cubed times e to the power of tx, right? Because the same process will apply. Every time we take the derivative of e to the power of tx, we get e to the power of tx times x. And when that new x combines with the x's waiting for us there, we get a higher power of x. So we started with x to the power of 1, we got an x to the power of 2. In the third derivative, we'll have x to the power of 3. And we can already see that in the nth derivative, we're going to get x to the power of n times e to the power of tx. That's pretty cool. And this actually hides here the main intuition for why we use this random variable e to the power of tx in the moment generating function. Okay, so let's finally do the Maclaurin expansion of our function by applying this formula now that we have derived the derivatives. Okay, so f of t, which I'll also write it out as e to the power of tx, equals, first term is f of 0. So when we plug in 0 for t here, we'll get e to the power of 0, which is 1. Okay, plus f prime evaluated at 0. So when we plug in 0 for t in here, we will get e to the power of 0 for this term, for the exponential term, so that's 1 times x. So we'll just have an x left in the numerator over 1 factorial times t. Plus, when we evaluate the second derivative at 0, e to the power of tx will be 1, and we'll be left with just x squared in the numerator. And we're already noticing a really nice pattern here, because for the third one, we can already tell e to the power of tx will be 1, and we'll be left with just x cubed in the numerator, and we have 3 factorial in the denominator times t to the power of 3 plus ... Okay, so that's the Maclaurin expansion of this function of t that we've been looking at. Okay, now what happens if we took the expected value of both sides? So if we take the expected value of this expression here and the expected value of the expression on the right. Well, let's write it out. So we have the expected value of e to the power of tx, and it makes sense to take the expected value of it because e to the power of tx is a random variable for a set value of t. X is a random variable, and e to the power of tx is a deterministic function of a random variable, therefore it's also a random variable, so it makes sense to take the expected value of it. Okay, and then on the right side we have what? We'll use the linearity property of expectations. So with regards to the first term, expected value of 1, well, expected value of a constant is just a constant, so we'll write that as 1 plus, what do we have here? So let's just remind ourselves that the expected value of ax equals a times the expected value of x, where a is a constant. So t over 1 factorial is a constant in the sense that it's not a random quantity. T is not, there's no randomness to t. It's a parameter. We don't know its value, but it's a fixed value. There's no randomness to it. So we can treat it as a constant. So t over 1 factorial plays the role of a here. So then we're left with t over 1 factorial times the expectation of x. X is the only thing that's random here, right? Okay, and then we can keep going and applying the linearity of expectations. We'll get t squared over 2 factorial times the expected value of now x squared. Okay, that's nice. You see, the raw moments are popping up, plus t cubed over 3 factorial times the expected value of x cubed, plus and so on and so forth. Okay, so it's hard to miss the moments now. The raw moments are right here. But we still haven't made a connection between this infinite sequence of raw moments and the PDF of x. So now let's take a look at what we have here on the left side. It's the expected value of a random variable that is a deterministic function of the random variable x. And in section 2.2 we covered lotus. And let's suppose that x is a continuous random variable with the PDF given by f of x. Okay, well then lotus tells us that the expected value of this deterministic function of x will be given by the integral of this function of x times the PDF of x, not of e to the power of tx, right? That's the whole simplification that lotus gives us. And this is over the entire real line. And you see now that with lotus, the PDF of x enters the picture on the left side. So let me shift things around here just to make it more visually clear. Okay, I've now written everything on one line. So this equality here is given by lotus, right? Lotus tells us what the expected value of a deterministic function of x is. And this second equality here is the Maclaurin expansion of the function e to the power tx. Notice that lotus treats e to the power tx as a function of x, deterministic function of x, whereas Maclaurin on the right side, we're doing an expansion of this same expression, but when we treat it as a function of t. And now that we've written everything on one line, we can see the connection of the PDF and the moments, the infinite sequence of raw moments. I have just shifted up our first result to give us a little bit more room, and this expectation, the expected value of this random variable e to the power tx that we've been playing with, of course, happens to be what we call the moment generating function. And we'll denote it with a capital M. It's the moment generating function of x, and it's a function of t. And why do we call it moment generating? Well, let's see how we can obtain the, let's say, the first moment of it. Well, the algorithm says that in order for us to get the nth raw moment, we just need to take the nth derivative of the moment generating function and evaluate it at 0. Now let's use this algorithm to obtain the raw moment from the moment generating function. And the first thing that we will need is the first derivative of the moment generating function. So the first derivative. The derivative of 1 is 0, so we don't need to write anything for that. Now for the second term, the derivative of this expression with respect to t will be everything except for t, so we're left with 1 over 1 factorial times e, the expected value of x, plus the derivative of now this term with t squared will be 2 over 2 factorial times the expected value of x squared, And let's not forget a t, right? Because when we took the derivative of t squared, we got 2t. And the derivative of the term with t cubed will give us 3 over 3 factorial times the expected value of x cubed. And let's not forget a t squared, right? Because when we took the derivative of t to the power of 3, we got 3t squared. Okay, and we can already see the pattern, so let's write one more term here. I'll get 4 over 4 factorial times the expected value of x to the 4th power times t to the 3rd power plus ... And let's evaluate this first derivative of the moment generating function at 0. And what do we get? Well, we need to replace t with 0, and we see that all the terms except for the first one will drop, and we're left with just the first term, which is 1 over 1 factorial times the expected value of x. Okay, now let's look at the second derivative of the moment generating function. The second derivative will be given by what? The derivative of the first term here will give us 0. For the second term, we'll get everything other than t, so 2 over 2 factorial times the expected value of x squared plus the derivative of this next term here with t squared will give us what? We'll notice that this 2 from the exponent by the power rule will join the 3 in the numerator. So in the numerator we'll get 2 times 3 over 3 factorial times the expected value of x cubed. And let's not forget a t, right? Because the derivative of t squared is 2t. Okay, so we're good there. On to the next term. The derivative of this term, the 3 from the exponent will join the 4 in the numerator. So we'll get 3 times 4 over 4 factorial times the expected value of x to the 4th power times t squared plus ... And when we evaluate it at 0, we get, well, we need to replace t with 0 everywhere, and we see that all the terms other than the first one will drop, and we get 2 over 2 factorial times e to the power of x squared. Now let's have a look at the third derivative of the moment generating function, and the pattern I think should be apparent. The derivative of this first term is 0. The derivative of the second term will give us everything other than t, which is what? We have 2 times 3 in the numerator. And notice that we could put a 1 in here, right? And effectively then in numerator we have 3 factorial. And we have 3 factorial in the denominator as well. So let's write it as 3 factorial over 3 factorial times e, the expected value of x cubed, plus the derivative of this term here with t squared. Notice that this 2 is going to join the 3 and the 4 in the numerator, and thus building the 4 factorial. And notice that the 4 factorial in the denominator has been sitting there all along since the Maclaurin expansion. But the 4 factorial in the numerator has been cooked to order via the power rule of differentiation. We have a 2 joining the 3 and the 4 in the numerator over 4 factorial. Might as well put a 1 in the numerator there. So effectively then in the numerator we have 4 factorial. Times the expected value of x to the 4th power times t plus ... And when we evaluate it at 0, when we evaluate the third derivative at 0, we'll get the third raw moment as 3 factorial over 3 factorial times expected value of x cubed. And now that we understand the pattern a little bit, we could go back to these second and first row moments that we derived and just make the numerators factorial. So instead of 2, we make it a 2 factorial. Instead of a 1 in the numerator, we make it a 1 factorial. It doesn't change the result, but it's cleaner now that we understand that the nth derivative of the moment generating function evaluated at 0 effectively gives us n factorial over n factorial times the expected value of x to the power of n. But of course, n factorial over n factorial cancels and we're just left with the raw moment. Now let's put this theory into practice with an example. Suppose that x has the exponential 1 distribution, which means that its PDF is given by e to the power of minus x, and its support is the part of the real line where x is greater than or equal than 0. And recall that what this means is that for x greater than or equal than 0, the PDF will be strictly greater than 0, and anywhere else, that is for x strictly less than 0, the PDF will be exactly 0. Okay, now let's try and find the MGF of this random variable. So the MGF of x will be a function of t. And how do we get the MGF? Well, we said that we will form a new random variable from x that is a deterministic function of it. That random variable is e to the power tx, and that will take its expected value. We can use Lotus to unfold this expected value, and Lotus tells us that it will be the integral of the function itself, e to the power tx, times the PDF of x. And we need a dx since we're integrating with respect to it. And this integral goes over the entire real line. But the support of the random variable is over the positive numbers, so let's break this integral into two. One where we're going from negative infinity to 0, and another one where we're going from 0 to positive infinity. And I'm doing that just to highlight the fact that we could have written this integral here just over the support of the random variable x. We don't need to go over the entire real line. And that's because outside the support, which corresponds to this integral, the PDF will be exactly 0, and therefore this integral will be 0. So we didn't have to write this part. So all we needed to write is just the integral going over the support of the random variable x. Okay, so let's replace the value of the PDF in there. So we have the integral from 0 to infinity of e to the power tx times, and the PDF expression is that e to the power minus x dx. Now let's combine the exponents, and in fact we can factor a minus x in the exponent, and we're left with 1 minus t, and we have a dx. Okay, and how do we integrate this? So first, let's see that this reminds us of the power rule, right? And so I think that if we put a 1 over 1 minus t in front, that should do it. Now this is the place where we need to be very careful. So let's take a moment to study this expression here for 3 different values of t. And in particular, it's this exponential term on the right here that will be tricky, so let's just study that one in isolation. When t equals minus 2, that exponential term becomes e to the power minus x times 1 minus minus 2, which is 1 plus 2, And so what we get is e to the power minus 3x. And notice that we'll be letting x go to positive infinity and 0. And as x will go to positive infinity, this expression will go to 0. And as x will go to 0, this expression will go to 1. Okay, so that looks good for t equal to minus 2. What about for t equal to 1? Notice what happens for t equal to 1. First of all, in this expression in front of the exponential, we would get a 0 in the denominator. And we don't even need to go any further. For t equal to 1, we're in trouble. So we do not want to allow t to equal 1. Okay, and so the first one was okay, the second one was not. And what about for t equal to 2? When t equals 2, this exponential expression becomes e to the power minus x times 1 minus 2. And that's e to the power minus x times minus 1, which is e to the power of x. And as we let x go to infinity, this expression will go to infinity. It will diverge. And as we let x go to 0, it'll go to 1. So we're in trouble here as well. So for what values of t are we okay? Notice that the values of t for which we're okay are the values corresponding to this expression 1 minus t being strictly greater than 0. Because when 1 minus t is greater than 0, we end up getting a negative sign in the exponent, and this expression converges. So 1 minus t greater than 0 is same as saying that t must be less than 1. And whereas for t equal to 1, we've seen that we're in trouble, and for t greater than 1, we're also in trouble. Okay, so what does that mean for us? It means that we can continue, but only for values of t less than 1. Now let's see what happens when x goes to infinity. Because we're only considering the cases when t is less than 1, 1 minus t will be greater than 0, and therefore, as x goes to infinity, we'll end up with negative infinity in the exponent, and e to the power of negative infinity will give us 0. So we have a 0 for the first part as we let x go to positive infinity. And then when we let x go to 0, in the exponent here, we're going to end up with 0. E to the power of 0 is just 1. So we're left with just this term up front here, which is minus 1 over 1 minus t, and that's 1 over 1 minus t. But we have to add this caveat here, that this is only for values of t less than 1. For other values of t, the integral that represents the moment generating function diverges. Okay, and this is the perfect place for us to be precise about when we say that a moment generating function exists. In the case of a continuous random variable x, the moment generating function of x is given by the expression in A. This is by Lotus, right? We've already seen that. However, we will say that the moment generating function of x exists only if this integral will converge for all values of t in a neighborhood of 0. Now let's go back to our example for a minute. We've obtained that this is the function corresponding to the MGF for t, and it converges for t less than 1. Okay, so here's 0, we're plotting values of t here, and here's 1, so 1 is excluded. Other than that, it converges for all values of t less than 1. Therefore, we can pick an interval around 0,
such that for all values of t, the moment generating function converges around 0. So we're fine. What would not have worked is if we had ended up with, say, a function that converges for all t less than minus 0.5, for example. Then that would mean that we obtain that convergence condition is that t is less than minus 0.5, which means that there is no neighborhood around 0 such that the MGF converges for all values of t. If you want to see an example of this, you can take a look at the log normal, because for the log normal it converges only for t less than or equal than 0, but it diverges for any positive t, and therefore, once more, there is no interval around 0 such that for all values of t, the MGF converges. So in that case, we say that the MGF of the log normal does not exist. Here, for the exponential, we're okay, so we say that the MGF of the exponential does exist. And let me just point out one other thing, that if we had a random variable y with the gamma 3, 1 distribution, we could go through the exact same process of deriving the moment generating function, and we would see that the moment generating function of this random variable y as a function of t is equal to 1 over 1 minus t to the third power for t also strictly less than 1. And notice that this MGF is the MGF of the exponential 1 basically raised to the third power, right? Let's just plant that in our heads, and we'll see later on why that's interesting. Let's briefly recap what we have achieved so far. We have shown that for the exponential 1 distribution, when we applied the definition of the moment generating function, we had to evaluate this integral, and when we evaluated it, we obtained this function 1 over 1 minus t. Importantly, and this is key, we did not conclude at this point that the moment generating function exists. We can only say that the moment generating function exists if this function that we obtain here after we do this integration exists or converges for all t in a neighborhood of 0. There has to be a neighborhood of 0. In other words, it should exist for some negative and some positive numbers and for 0. Given that the function we obtained exists for all t less than 1, we could pick our neighborhood to be between minus 0.5 and 0.5, and this function we obtained exists or converges for all t in this neighborhood. Therefore, we will say that the moment generating function of the exponential 1 distribution exists. We found it right here. There are many reasons to underscore that we have to establish that a moment generating function exists. I'll mention two key ones. If the moment generating function of a distribution exists, then it uniquely identifies that distribution. That's one. And two, if the moment generating function of a distribution exists, then it can also be uniquely identified by the infinite sequence of raw moments. Those are two very big results. So once we've established that the moment generating function exists, we have opened the door to a lot of exciting things that we can do now. But first things first, let's do the Maclaurin series expansion of the moment generating function. So we have seen that the Maclaurin series expansion would look like this. The first term is the moment generating function evaluated at 0 plus the first derivative of the moment generating function evaluated at 0 times t over 1 factorial plus the second derivative of the moment generating function evaluated at 0 times t squared over 2 factorial plus the third derivative of the moment generating function evaluated at 0 times t cubed over 3 factorial plus, and so on and so forth. And we could write it as a summation as well, as the sum of the moment generating function of x evaluated at 0 when we take its nth derivative, where this n is going to go from 0 to infinity times t over t to the power of n over n factorial. Let's check if this is correct. When n is 0, we take the 0th derivative. Basically means we do not take the derivative, we take the moment generating function as is. And t to the power of 0 is 1, and 0 factorial is 1. So when for n 0, we get the first term, which is just the moment generating function evaluated at 0. When n is 1, we get this second term here, the first derivative of the moment generating function evaluated at 0 times t to the power of 1 over 1 factorial. So that looks correct. And we've seen that alternatively this can be written in terms of raw moments, where now instead of the nth derivative of the moment generating function evaluated at 0, we'll write the raw moment, which is the expected value of x to the power of n times t to the power of n over n factorial. Okay, so now in order for us to do this Maclaurin expansion for our moment generating function of the exponential 1, we'll need to find these terms, the first derivative of the moment generating function, the second, the third derivative, and so on and so forth. So let's do that. Let's see, what is the first derivative of the moment generating function? Well, the moment generating function is this, which could be written as 1 minus t to the power of minus 1. So its first derivative by the power law will be minus 1 times 1 minus t to the power of minus 2. And by the chain rule, we have to take the derivative of 1 minus t, and that is minus 1. So when we put it together, we get 1 minus t to the power of minus 2. And what's the second derivative of the moment generating function? It's minus 2 times 1 minus t to the power of minus 3 times a minus 1, and that is 2 times 1 minus t to the power of minus 3. And the third derivative is 2 times minus 3 will give us minus 6. But rather than writing minus 6, I'll keep these separate. So we got a minus 2 times 3 times 1 minus t to the power of minus 4. And by the chain rule, we need a minus 1. And that will give us 2 times 3 times 1 minus t to the power of minus 4. And let's do one more. The fourth derivative of the moment generating function is minus 2 times 3 times 4 times 1 minus t to the power of minus 5 times a minus 1, and we get 2 times 3 times 4 times 1 minus t to the power of minus 5. And we can now recognize something. 2 times 3 times 4 is 4 factorial. So what we have is 4 factorial times 1 minus t to the power of minus 5. And this here was 3 factorial times 1 minus t to the power of minus 4. And this was 2 factorial times 1 minus t to the power of minus 3. And finally, this was 1 factorial times 1 minus t to the power of minus 2. And we need to evaluate all of these at 0. including the moment generating function itself, right? Because all these terms in the Maclaurin series are evaluated at 0. So the moment generating function evaluated at 0 would give us what? We have to replace 0 for t in here. We get 1 over 1, which is 1. The first derivative of the moment generating function evaluated at 0 would give us what? We have to replace 0 for t in here, and we get 1 factorial. And notice that will be the case for all these terms. 1 minus t to any power is going to give us just 1 when we evaluate it at 0. So the second derivative will give us just this term in front, which is 2 factorial. The third derivative evaluated at 0 will give us 3 factorial. And the fourth derivative evaluated at 0 will give us 4 factorial. And we're finally ready to do the Maclaurin expansion of the MGF. And what is it that we get? We get 1 for the first term, plus we replace 1 factorial for the second term, and we get 1 factorial times t over 1 factorial. And I'm going to circle this term because this is the first raw moment, right? Plus, what is the second derivative evaluated at 0? It's 2 factorial times t squared over 2 factorial. And again, I'm going to circle the first term because this is the second raw moment, plus 3 factorial, which comes from here. The third derivative evaluated at 0 is 3 factorial times t to the third power over 3 factorial. And I'm going to circle 3 factorial because that's the third raw moment, plus, and so on and so forth. Then now, imagine that we were interested in the 1245th moment. Well, we could read it from here and we can see from the pattern that it'll be 1245 factorial. We are now ready to see something that I think is incredibly cool and fundamentally one of the main points that the authors are trying to get across in this second chapter. From the definition of the moment generating function, we know that it is this expression. It's an integral, and the PDF of the random variable enters this integral, right? And on the other hand, we have shown that the moment generating function can be represented using the Maclaurin sequence as an infinite sum of terms, and from these terms we can read off the moments. So we have an infinite sequence of moments. When the moment generating function exists, as it does for the exponential 1 distribution, the PDF and the infinite sequence of moments and the MGF are different representations of the same underlying probability function induced by the random variable x. In place of the PDF here, we could write the derivative of the CDF, right? Because that's how we obtain the PDF, by taking the derivative of the CDF. So the first representation of that probability function is via its CDF. The second representation is via the PDF. The third representation of the same probability law is via the MGF. The fourth representation is via this infinite sequence of moments. And there is a fifth representation that is mentioned in this section, and that is via the characteristic function. The moment generating function is a Laplace transform of the PDF. So essentially what we do here to the PDF is a Laplace transform. That's how we send it from the PDF universe to the MGF universe. The characteristic function is similarly a transform of the PDF. It's just that it's a different one. It's the Fourier transform. It's more complicated. It will involve complex analysis. So we won't go into it in depth, but it's worth noting that there is a fifth universe. So keep these 5 universes in mind. If we look at the first universe, that of the CDF of the exponential 1 distribution contains the exact same information as does the PDF in universe 2, as does the MGF in universe 3, as does the infinite sequence of moments in universe 4, and as does the characteristic function in universe 5. Provided the MGF exists, and provided that we're dealing with an absolutely continuous random variable or a discrete one, so that the PDF exists and can be derived from the CDF. Now this means that if we are trying to prove something about a random variable or a sum of random variables, we could do it in any of these 5 universes. For example, in a moment we'll look at the sum of 3 exponential 1 random variables, and we will work with it in the MGF universe. We will find that the MGF of this sum is exactly the MGF of a gamma 3-1 distribution, and from that we will conclude that the distribution of the sum of 3 exponential 1 random variables is a random variable that has a gamma 3-1 distribution. We've worked in the MGF universe with that one because it lends itself most easily to this particular problem. We could have attacked it in any of these universes. We could have gone with the CDFs, although it's much harder because it involves the convolution of random variables. We could have tried to establish the same result in the PDF space, and we should find that the PDF of the sum of 3 exponential 1 random variables is the PDF of the gamma 3-1 distribution. That result must hold. It's just that it might be harder to get there. Same thing in the CDF space, we must find that the result is that the CDF of that sum is the CDF of the gamma 3-1 distribution. It's just that it might be maybe more work attacking this particular question in the CDF universe. We could have also looked at the infinite sequence of its moments or used the characteristic function. It is difficult to oversell how important a moment we find ourselves in right now that we can perceive these 5 universes. We're only in chapter 2, but the doors that have already opened to us via these 5 universes are incredibly powerful. The existence of these 5 universes is something that the authors of this book have very carefully woven into chapter 2. And something else that they have very carefully hidden for us is the following. If this cloud were to represent the dependent random variables out there, this much smaller cloud would represent the independent random variables out there, reflecting the fact that in the real world most random variables are dependent. But here's the thing. So far, we have only looked at this green circle because we have looked at only one type of dependent random variables, and that is the deterministically dependent, as opposed to those that are stochastically dependent. In section 2.1, we learned how to find the distributions of random variables that are deterministic functions of a random variable x. Right, so we learned how to find the PDF of a random variable y using the change of variables formula. In section 2.2, we learned how to find the expected value of random variables that are deterministic functions of another random variable. In section 2.3, we've introduced the MGF, and that may seem like we've introduced something new, but notice that the MGF is the expectation of a random variable that is a deterministic function of another random variable. So we're very much building our knowledge here by the bootstraps from what we learned in sections 2.1 and 2.2. So one really cool realization, I think, is that so far we have only looked at random variables that are deterministic functions of each other. To bring one more evidence to make this point, in theorem 225, the authors have shown that the expected value of a linear combination like this, which has a times g1 of x, some deterministic function of random variable x, plus b times g2 of x plus c, and we're told what it's equal, the fact that the expectation is a linear operator. Okay, and the point I'm making here is that this result is true more generally. For any random variables, x and y, such that these random variables admit a joint distribution. But the moment we introduce two different random variables with potentially different sources of randomness, we need to introduce the concept of a joint distribution. And although this same result holds, notice that the authors were very careful not to take us there yet, because they wanted to introduce here only the random variables that are deterministically dependent. But amazingly, look at how much we can already do, having looked at that just this tiny sliver of the probability universe. Let us, for just one brief moment, depart this island of deterministic dependence and look at the island of independent random variables. And the reason for doing so is that one of the main superpowers of MGFs applies to independent random variables. So let's have a look at that. Suppose that we are working with random variables x1, x2, and x3, which are independent and identically distributed as exponential 1 random variables. We have shown that in the case of the exponential 1 distribution, the moment generating function exists. So let's just note that down. And we know exactly what it equals. In each of these cases, the moment generating function we've shown to be 1 over 1 minus t. Now suppose that our work has us examine the sum of these three random variables, x1 plus x2 plus x3, and we need to know what the distribution of z is. In chapter 4, we will introduce a theorem which says that the moment generating function of the sum of independent random variables equals the product of the moment generating functions of these. So if we want the moment generating function of the random variable z, we just have to multiply out these moment generating functions, and each of these equals 1 over 1 minus t, and that of course could be written alternatively as 1 over 1 minus t to the third power, and we are done. This is the moment generating function of the random variable z. Oh, but we have shown that the moment generating function of a random variable w, where w has the gamma 3,1 distribution, is exactly that, 1 over 1 minus t cubed. Therefore, the sum of three independent random variables, each of which has the exponential 1 distribution, has the gamma 3,1 distribution. Because the MGF of the gamma 3-1 distribution exists, that means that there is no other distribution out there with the exact same MGF. So if we stumble now upon this MGF, it must belong to that of the gamma 3-1 distribution. Pretty amazing. And look how easy it has been. This problem would have been much more difficult in any of the other universes. We could have tried this in the PDF universe, and there is a formula for the convolution of two random variables. In other words, we could have derived the PDF of x1 plus x2 first, using the convolution formula, and then take that result and say we call x1 plus x2, let's call that z1, and then we would have to take the convolution of z1 and x3, so we'd have to apply the convolution formula 2 times in order for us to get the PDF of the sum of 3 random variables, and that would not have been straightforward. But in the end, we can guarantee that we will have reached the same conclusion. We will have found that the PDF of Z is exactly the PDF of the gamma 3-1 distribution, and we will have established the same result. Or we could have approached this in the CDF world, where we could have investigated the CDF of x1 plus x2 plus x3, and we will have found the same thing, that the CDF of the sum happens to be the same as the CDF of the gamma 3-1 distribution, and therefore this sum has the gamma 3-1 distribution. And we could also have approached this in the other two universes, using characteristic functions or using the infinite sequence of moments. When the moment generating function exists, and if we're dealing with absolutely continuous random variables or discrete random variables so that the PDF PMF exists, these 5 universes will tell the same story, and the uniqueness property says that we can approach a problem in any of these universes and we should get the same answer. So then, depending on the question at hand, we can see in which of these universes would the solution be most straightforward. In this particular case, the moment generating function universe was the obvious choice. Now let's return to the opening puzzle where we looked at two PDFs that have the same infinite sequence of moments and yet are completely different PDFs and look completely different. The problem with these is that neither of these admit an MGF. In other words, the MGF does not exist in the neighborhood of 0 for both of these. And when a distribution does not have an MGF, this uniqueness between the 5 universes breaks down. In particular, the infinite sequence of moments no longer uniquely identifies a distribution. In this case, we have 2 random variables that have the same infinite sequence of moments and yet are different distributions. So it's one of those cases where if we're looking at distributions that do not admit an MGF, we just have to be careful. There are a couple of famous distributions that do not have an MGF, such as the Cauchy, but for the most part, we'll be working with distributions where the MGF will exist, and this ability for us to go between these 5 universes will be key. And that's it for section 2.3 on moments and moment generating functions. The next section is on differentiating under an integral sign. It's really all about mathematics there. There's really no probability content. And I will not cover this section now because I don't think we will stumble until we get to chapter 7, on a single case in which we will need to be careful about differentiating under an integral sign. Until then, we can just assume that we can and move forward, and I'll be careful in chapter 7 to point out that we cannot take differentiating under an integral sign for granted. So if chapter 1 was all about random variables and CDFs and PDFs, then chapter 2 was all about distributions of functions of random variable, and we learned about the change of variables formula in section 2.1, which allows us to derive their distribution. And in section 2.2 we learned about how to calculate their expected values, and in section 2.3 we learned about moment generating functions of random variables, and we have now seen the existence of these 5 universes, which will allow us to tackle the same problem in any of these 5 universes, assuming that uniqueness property. In the next chapter, we'll cover the common families of distributions. You can think of this as the Hollywood of probability theory. These are the families of distributions that are most often used and will motivate each. And it won't be long after that we'll get to chapter 4, and we'll cover multiple random variables. We'll start by introducing what the joint distribution is, which will allow us then to define what independent random variables are, what dependent random variables are, and that will be the first time that we will tackle problems involving more than one random variable that are not simple deterministic functions of each other. Okay, that's the plan. Thanks for watching. I'll see you in the next video.